Happy learning to everyone. I am Dr. K. Mohana, Assistant Professor in Mathematics, Nirmala College for Women, Coimbatore. Through this video, I am going to explain about Banach space. Before defining Banach space, we will learn what is normed linear space. Let N be a linear space over R or C. A norm is a function from N to R satisfying the following conditions. First condition, norm x always greater than or equal to 0. Norm x is equal to 0 if and only if x is equal to 0. Norm x plus y always less than or equal to norm x plus norm y. Norm alpha x is equal to mod alpha into norm x. Norm x denotes the length of the vector x. The linear space N with the norm is called the normed linear space. Let us have some remark using normed linear space. Every normed linear space is a metric space where g of x comma y is equal to norm x minus y. We will have the proof for the above statement. D of x comma y is always greater than or equal to 0. So it satisfies the first condition of the normed linear space. For the second condition, d of x comma y equals 0 if and only if norm x minus y is equal to 0 if and only if x minus y equal to 0 if and only if x always equals to y. And third condition, d of x comma y is equal to norm x minus y, which can be written as norm of minus of y minus x, which is equal to, and minus 1 can be taken out, so it is actually alpha. So mod minus 1 norm y minus x, which is equal to modulus of minus 1 value always plus 1 norm y minus x as it is. So which is equal to norm y minus x, which is equal to d of x minus y, x comma y. And the fourth property, d of x comma z is equal to norm of adding y and subtracting y. I can write it as norm x minus y plus y minus z, which is less than or equal to norm x minus y plus norm y minus z, which can be written as in terms of d, which is less than or equal to d of x comma y plus d of y comma z. Hence, every normed linear space is a metric space. The second remark, norm x minus norm y, the whole modulus is less than or equal to norm x minus y for every x comma y belongs to capital N. Norm x is equal to norm of x minus y plus y. That means we are adding and subtracting y value inside the norm. So which is less than or equal to norm of x minus y plus norm y. So you take the norm y value to the other side. So norm x minus norm y is less than or equal to norm x minus y. So which is equation number 1. And we will consider the next part, norm x minus norm y. Modulus of norm x minus norm y is equal to norm y minus norm x. So which is also less than or equal to modulus norm of y minus x, which can also be written as norm x minus y. So therefore, modulus of norm x minus norm y is less than or equal to norm x minus y. This is equation number 2. So from 1 and 2, I can say it as modulus of norm x minus norm y is less than or equal to norm x minus y. And the next definition, in a normed linear space N, we say xn tends to x if norm xn minus x tends to 0 as n tends to infinity. Given epsilon greater than 0, there exists n naught, capital N naught, such that norm xn minus x is less than epsilon for every small n is greater than or equal to capital N naught. So this result is true for all the normed linear space N. So we have a note here, a linear space with a metric, which is a metric space, is called normed linear space or normed vector space. Going for the third remark, prove that norm is a continuous function. So what I have to prove? To prove xn tends to x, which implies norm xn also tends to norm x. So by using the previous remark, modulus of norm x minus norm xn minus norm x is always less than or equal to norm xn minus x, which tends to 0 when n tends to infinity. So that means norm x n minus norm x tends to 0 as n tends to infinity, which implies norm xn tends to norm x as n tends to infinity. So from this we can conclude that norm is a continuous function. We'll move to the next remark. Addition and scalar multiplications are jointly continuous. We have a proof for this. Let xn tends to x, which implies norm xn minus x tends to 0 as n tends to infinity. Yn tends to y, which implies norm yn minus y tends to 0 as n tends to infinity. Now we have to prove that xn plus yn tends to x plus y. So you consider the following. So norm xn plus yn minus x plus y, which is equal to norm xn minus x plus yn minus y, which is less than or equal to norm of xn minus x plus norm of yn minus y, which tends to 0 as n tends to infinity. Therefore, which can be written as norm of xn plus yn minus x plus y, which tends to 0 as n tends to infinity. From this I can say it as xn plus yn tends to x plus y. Let us assume that xn tends to x, so which implies norm xn minus x tends to 0 as n tends to infinity, and alpha n tends to alpha, which implies norm alpha n minus alpha tends to 0 as n tends to infinity. Now I have to prove alpha n xn tends to alpha x. So that is to prove norm alpha n xn minus alpha x tends to 0. So you consider norm alpha n xn minus alpha x, which is equal to norm alpha n xn minus alpha n x plus alpha n x minus alpha x. I am just adding and subtracting alpha n x here. So which is equal to norm alpha n xn minus x plus x into alpha n minus alpha. And alpha n can be taken outside because it is a scalar. Modulus of alpha n into norm xn minus x plus modulus of x into modulus of alpha n minus alpha into norm x, which tends to 0 as n tends to infinity. So which implies that norm of alpha n xn minus alpha x tends to 0 as n tends to infinity. So from this we can conclude alpha n xn tends to alpha x. And here we have the definition of Banach space, a complete normed linear space. Whenever the normed linear space is complete, then we can call that space as Banach space. And using the Banach space, we have proved the following theorem. Let M be a closed linear subspace of a normed linear space N if the norm of coset x plus capital M is the quotient space N slash M is defined by norm x plus M is equal to infimum of norm x plus small m, where for all small m belongs to the capital M quotient space. So the n by m is also a normed linear space. So this is what we have to prove. Further, if n is a Banach space, then n by m is also a Banach space. So you write the given assumptions here. So given that n by m, which is defined by norm x plus m, which is equal to infimum of norm x plus m, such that x plus m belongs to capital M. So by the definition of norm, I can say that modulus of norm of x plus m is greater than or equal to 0 always. And going to the second proof, second property of the proof, let norm x plus m is equal to 0, which implies that infimum of norm x plus capital M, which is also 0. So the whole thing is equal to 0. So infimum value also equals to 0. So there exists a sequence small mk in capital M such that norm x plus mk tends to 0, which implies mk tends to minus x, which implies minus x also belongs to capital M. So which implies x plus capital M is a 0 element in n slash M. And the next part of the property of the third property proof here, norm x plus m plus y plus m equals to norm x plus y plus m, which is equal to infimum of infimum over small m belongs to capital M, norm x plus y plus m. So that one m can be written as m1 and m2. So in terms of m1 and m2 I can write, so infimum of m1 comma m2 belongs to capital M, modulus norm of x plus y plus m1 plus m2, which is less than or equal to. So if when I split the norm, then I will have less than or equal to. So less than or equal to m infimum over m1 belongs to capital M, norm x plus m1 plus infimum over m2 belongs to capital M, norm y plus m2. So which is less than or equal to norm x plus capital M plus y plus capital M. Next, I am going to prove the fourth property, that is norm alpha of x plus capital M is equal to norm alpha x plus capital M, which is equal to infimum m belongs to capital M, norm of alpha x plus small m, which belongs to capital M, which is equal to infimum over m1 belongs to capital M, norm alpha x plus alpha m1, which is equal to infimum m1 belongs to capital M, norm of alpha of norm x plus m1, which is equal to modulus of alpha infimum over m1 belongs to capital M, norm x plus m1, and which is equal to modulus of alpha norm x plus capital M, which from this I can say n slash m is a normed linear space. And I have to prove this capital N is complete, then only I can say it as it is a Banach space. So let capital N be complete, and to assuming this N is complete, I have to prove N slash M is also complete. So take a Cauchy sequence in N by M. So to prove this sequence has convergent subsequence. So it is possible to find the subsequence x plus capital M of the original Cauchy sequence such that norm x1 plus capital M minus x2 plus capital M, which is less than half, and norm x2 plus capital M plus x3 plus capital M is less than 1 by 2 square, etc. So the nth term will be norm xn plus capital M minus xn plus 1 plus capital M is less than 1 by 2 power n. So choose any vector in this and select a vector y2 in x2 plus m such that norm y1 minus y2 is less than half. So next to select the vector y3 in x3 plus m such that norm y2 minus y3 is less than 1 by 2 square. So continuing this way, we get a sequence yn and yn plus 1 in capital N such that norm yn minus yn plus 1 is less than 1 by 2 to the power of n. So if m is less than n, then norm ym minus ym minus yn is equal to norm ym minus ym plus 1 plus ym plus 1 minus ym plus 2, etc. The last term will be yn minus 1 minus yn. So which is less than or equal to. So when inside the norm term we have multiples of terms. So I am going to split that term. So if I split the norm, then I will have less than or equal to. So which is less than or equal to norm ym minus ym plus 1 plus norm ym plus 1 minus ym plus 2, etc. The last term will be norm yn minus 1 minus yn. So which is less than or equal to 1 by 2 power m plus 1 by 2 power m plus 1 plus etc. 1 by 2 to the power of n plus 1. So I can have 2 power m term outside. So 1 plus half plus 1 by 2 square plus etc. So which is also less than or equal to 1 by 2 power m divided by 1 by 1 minus r. That means 1 by 1 minus half. So which is nothing but 1 by half is denominator will go to the numerator. So I can write it as less than or equal to 1 by 2 power m into 2. So 2 can be cancelled. So which is equal to 1 by 2 power m minus 1, which tends to 0 as m tends to infinity. So the right hand side tends to 0, then automatically the left hand side also tends to 0. That is norm ym minus yn tends to 0 as m tends to infinity. Therefore, the yn sequence yn is a Cauchy sequence in n. Since n is complete, there exists a vector x in capital N such that yn tends to x, and now norm xn plus m minus x plus m is less than or equal to norm yn minus x, which tends to 0. So therefore xn plus m tends to x plus m. So therefore n by m is also complete. Therefore already we have proved that n by m is a non-linear space. So we can say that n by m is non-linear space and it is complete. Therefore it is a Banach space. So example for the Banach space I have proved here. Prove that LP is a normed linear space and also Banach space. So let P be a real number. There exists 1 less than or equal to P less than or equal to infinity. Let 1P be the space of all sequences. Small LP be the space of all sequences x is equal to x1, x2, etc. xn with the property that sigma I from 1 to infinity modulus of xi to the power of p is less than or equal to infinity. We can prove that LP is a Banach space under the norm x over p is equal to sigma I from 1 to infinity modulus of xi power p to the power of 1 by p. So to prove norm P is a normed linear space, so obviously norm x is greater than or equal to 0 and norm x over P is equal to 0, which implies that sigma xi to the power of P to the power of 1 by P is also equal to 0. So which implies that xi should be equal to 0 if and only if x is equal to 0. And the third property of the normed linear space is norm x plus y over P is less than or equal to definitely using the inequality norm x over P plus norm y over P. So hence we get the third property also. And the fourth one, norm x alpha x over p is if and only if sigma I from 1 to infinity modulus of alpha xi to the power of p to the power of 1 by p equals 0 if and only if alpha can be taken out, the remaining you can keep it inside. So modulus of alpha norm x over p. So therefore LP is a normed linear space. So to prove LP is a Banach space, already I have proved that it is a normed linear space, and now we are going to prove it is a Banach space as well. So when you want to prove it is a Banach space, first you have to prove the normed linear space and you have to prove the completeness. So if normed linear and complete, then we can say the same space is called Banach space. So LP is a Banach space I have to prove now. So you consider the Cauchy sequence xn, then where xn is equal to x1 power n, x2 power n, etc. So you just assume epsilon is greater than or equal to 0. There exists n naught such that norm xn minus xm over p is less than epsilon. For every n comma m is greater than or equal to n naught. So from the given definition, so norm of xn minus xm can be written as sigma I from 1 to infinity modulus of xi power n minus xi power m to the power of p to the power of whole to the power 1 by p, which is less than epsilon. So which implies that modulus of xi power n minus xi power m is less than epsilon for every n m greater than or equal to n naught. So therefore xi power n from 1 to infinity is a Cauchy sequence in R. Since R is complete and we can take the limit m tends to infinity in the equation number 1. So we can have modulus of xn minus x over p is less than epsilon for every n is greater than or equal to n naught. Therefore xn tends to x. So now next we are going to prove x belongs to LP. So which implies norm x over p is less than or equal to norm x minus xm over p plus norm xm over p. So this is nothing but which is less than epsilon plus capital M, which is less than infinity. Therefore x must be belongs to LP. Therefore LP is a Banach space. So hope all of you enjoyed this video. Thank you for watching this video.